Section 1 Introduction. Over the last 10 years, the ability to train large artificial neural networks has advanced significantly, particularly following the introduction of the transformer architecture. Despite this progress, our understanding of the underlying principles is somewhat limited. Amidst a plethora of results, we've noticed a pattern, typically coinciding with the advent of transformers, that shows that the performance of these networks improves as we either increase computational resources or expand the network size. This trend is known as scaling laws. These scaling laws have been the compass guiding our deep learning exploration of scale. Variations of these laws have led to noticeable performance leaps. In this study, we build upon the work of Eldon and Lee, exploring a different aspect, the data quality. It's a well-established fact that better quality data yields improved results. For instance, data cleaning, a crucial part of modern dataset creation, can result in additional benefits such as reduced datasets or more iterations over the data. Eldon and Lee's recent work on Tiny Stories, a high-quality synthetic dataset used to teach English to neural networks, showed that superior data quality could drastically alter the scaling laws, potentially enabling leaner models to perform at the same level as large-scale ones. We go a step further in this study, revealing that high-quality data can enhance the state-of-the-art, SOTA, of large language models, LLMs, while significantly cutting down dataset size and computational requirements during training. Importantly, leaner models that require less training can substantially lower the environmental impact of LLMs. We concentrate on LLMs designed for coding, specifically those that generate simple Python functions from their docstrings. We use the HumanEval benchmark, commonly employed to compare ILM's performance on code. We demonstrate how high-quality data can disrupt existing scaling laws by training a 1.3 billion parameter model, which we name Phi1, for approximately 8 iterations over 7 billion tokens, slightly more than 50 billion total tokens observed, and then fine-tuning it on less than 200 million tokens. In a nutshell, we pre-train on textbook quality data, both synthetically produced, with GPT 3.5, and extracted from online sources, and we fine-tune on textbook exercise-like data. Despite being significantly smaller than rival models in terms of dataset and model size, we achieve 50.6% pass at 1 accuracy on HumanEval and 55.5% pass at 1 accuracy on MBPP, mostly basic Python programs, one of the top self-reported scores using only a single generation of LLM. We detail our training process and discuss the crucial role our data selection process played in achieving this outcome. Interestingly, even though Phi1 has been trained on far fewer tokens compared to existing models, it still exhibits emergent properties. We discuss these properties and validate the theory that the number of parameters plays a pivotal role in the emergence of these properties, as we compare the outputs of Phi1 with those of Phi1 small, a model trained using the same method but with only 350 million parameters. This approach aligns with the Sparks of AGI paper, which advocated shifting away from static benchmarks to assess ILM's performance. Lastly, we discuss alternative benchmarks for evaluating our model and investigate potential contamination of our training data with respect to HumanEval. Section Summary. The success of training large artificial neural networks has been attributed to scaling laws, which predict that performance improves as the amount of compute or network size increases. However, this paper explores the impact of high-quality data on the performance of large language models, LLMs, trained for code, demonstrating that it can break existing scaling laws and significantly reduce the environmental cost of LLMs. The authors trained a 1.3B parameter model on textbook quality data and achieved high accuracy on HumanEval and MBPP benchmarks, despite using a much smaller dataset and model size than competing models. Section. More related works. Our research contributes to the ongoing work that uses language learning models, LLMs, to create programs. Additionally, our method is part of a growing trend that involves using existing LLMs to generate data for training future LLMs. This concept, known as recursive training, has sparked a debate around whether it might limit the scope of the resulting LLM. However, our paper intentionally focuses on a narrow task. We hypothesize that by doing this, we could potentially achieve superior results compared to the teacher LLM on this specific task. We emphasize in the title of this study that high-quality data is a fundamental component for training our model. Unlike previous research that utilized traditional text data sources for generating code, e.g., the stack, which includes source code from repositories with liberal licenses, or other web-based datasets like Stack Overflow and Code Contest, we argue that these resources may not provide the optimal learning material for teaching the model how to logically plan and devise algorithms. Though our model architecture and training methodologies are rather standard, the focus of this section is primarily on how we curated our data. The conventional code datasets offer a vast and varied corpus covering an extensive range of topics and use cases. However, upon manually inspecting random samples, we observed that many of these snippets are not very instructive for learning basic coding. They frequently depend on external modules or files, consist of trivial or boilerplate code, contain algorithmic logic buried within complex or poorly documented functions, or disproportionately represent certain topics or use cases. We hypothesize that this unsystematic approach to learning coding can be frustrating and inefficient for a human learner. The data quality and quantity, the noise, ambiguity, and incompleteness all affect the learning experience and, we hypothesize, the performance of language models. We propose that language models would perform better with a training set that emulates a good textbook, meaning it should be clear, self-contained, instructive, and balanced. We directly tackle this issue in our work and demonstrate that with the intentional selection and generation of high-quality data, we can achieve unparalleled results on code generation tasks using a smaller model and less computation than existing methods. Our training relies on three primary datasets. 1. A filtered code language dataset, which is a subset of the stack and Stack Overflow, obtained using a language model-based classifier, comprising about 6 billion tokens. 2. A synthetic textbook dataset comprising less than 1 billion tokens generated by GPT 3.5 Python textbooks. 3. A small synthetic exercises dataset consisting of 180 million tokens of Python exercises and solutions. These datasets combined contain less than 7 billion tokens. We refer to the combination of the filtered code language dataset and the synthetic textbook dataset as the code textbook. We use this dataset in the pre-training phase to create our base model Phi1 base, which already shows a competitive HumanEval performance of 29%. We then use the CodeExercises dataset to fine-tune our Phi1 base model to create the Phi1 model. Despite the CodeExercises dataset's small size, fine-tuning with it is crucial for significant improvements, unlocking many exciting capabilities in our Phi1 model that weren't observed in Phi1 base. Section summary. The paper discusses the use of language models, LLMs, for program synthesis and the emerging trend of using existing LLMs to synthesize data for the training of new generations of LLMs. The authors argue that standard sources of text data for code generation, such as the stack and other web-based datasets, are not optimal for teaching the model how to reason and plan algorithmically, and propose a curated dataset of high-quality data for training their model. Section 2.1 Filtering of existing code datasets using a transformer-based classifier. Our first step involves filtering publicly available Python code datasets. For this purpose, we leverage the Python subset from two primary sources, the stack and Stack Overflow. Together, these contain more than 35 million files or samples, which make up over 35 billion tokens in total. Our objective is to identify the educational value of these samples for beginners learning coding concepts. For this, we select a small subset, approximately 100,000 samples, from the larger collection. We then utilize GPT-4, a language model, to tag these samples according to their educational value. Essentially, we feed a code snippet to GPT-4 and ask it to evaluate the snippet's usefulness for someone learning basic coding. After this annotation process, we use these rated samples to train a machine learning model known as a random forest classifier. This classifier's role is to predict the quality of a file or sample. It does this by using output embeddings, obtained from a pre-trained model, as features. Please note that while we do use GPT-4 for this annotation process, it's used sparingly and mainly as a way to avoid the tedium of manual human annotation. It's worth mentioning that GPT 3.5, a predecessor of GPT-4, is used more extensively elsewhere in our work to generate synthetic content. To provide a clearer understanding, consider the following examples of code snippets that GPT-4 rated for educational value. An example of a high educational value snippet is a piece of code that defines functions to perform an L2 normalization, compute Euclidean distance, and compute cosine distance. These are fundamental operations in many areas of machine learning and data science. On the other hand, a low educational value snippet is a block of code defining a class named default. The class involves a mix of initializations and attributes, but without context or further explanation. This example might be confusing or irrelevant for a beginner trying to learn basic coding concepts. Section summary. The authors use a transformer-based classifier to filter publicly available Python code datasets, such as the stack and Stack Overflow, containing over 35 million files, samples. They annotate a small subset of these files using GPT-4 to determine their educational value and train a random forest classifier to predict the quality of a file, sample using its output embedding from a pre-trained model as features. Section 2.2 Creation of synthetic textbook quality datasets. Section 2.2 Developing synthetic, textbook quality datasets. One of the major obstacles in crafting an excellent dataset for code generation is guaranteeing that the examples are varied and non-repetitive. When we refer to diversity, we're speaking about examples that encompass a broad spectrum of programming concepts, abilities, and situations. These examples should exhibit varying degrees of difficulty, complexity, and style. Diversity holds significance for several reasons. It exposes the language model to diverse methods of expressing and resolving coding problems, lessens the likelihood of overfitting or repeating specific patterns or solutions, and augments the model's ability to generalize and tackle new or unseen tasks. Yet, attaining diversity is not a straightforward task, particularly when relying on synthetic data produced by another language model. Merely prompting the model to generate a programming textbook or a series of exercises, even with slight variations in the instructions or parameters, might result in a highly homogeneous and repetitive dataset. This redundancy arises because language models typically gravitate towards the most likely or prevalent routes based on their training data and inherent tendencies, lacking the creativity or motivation to explore unique or alternative code generation paths. Therefore, we need to find an effective method that will stimulate the language model to display more creativity and diversity in its output, all while preserving the quality and coherence of the examples. We drew inspiration from a technique where a varied set of short stories were produced by introducing a random subset of words from a fixed vocabulary into the prompt. The technique required these words to be somehow incorporated into the generated text. We're seeking ways to introduce this element of randomness into the prompt in a manner that fosters the creation of a diverse dataset. Section Summary. Creating a diverse and non-repetitive dataset for code generation is a challenge. Diversity is important to expose the language model to different ways of expressing and solving problems in code, reduce overfitting, and increase generalization. Injecting randomness into the prompt, inspired by a method used to create diverse short stories, can induce the language model to be more creative and diverse in its output while maintaining quality and coherence. Section 2.3 Model Architecture and Training. We adopt a transformer architecture that primarily relies on a decoder for our model, implementing a method called flash attention to handle multi-head attention, MHA. This architecture also includes MHA and multi-layer perceptron, MLP, layers working in tandem, as seen in recent models like CodeGen, POM, and GPT-Neox. We've designed two models. The larger one, called the Phi1 model, holds 1.3 billion parameters, incorporating 24 layers, a hidden dimension of 2048, an MLP inner dimension of 8,192, and 32 attention heads, each with a dimension of 64. The more compact version, named Phi1 Small, comprises 350 million parameters. This one has 20 layers, a hidden dimension of 1024, an MLP inner dimension of 4096, and 16 attention heads, each also with a dimension of 64. Both models utilize rotary position embedding with a rotary dimension of 32. We decided on these structural elements based on previous research. We also employ the same tokenizer as the -350M mono model. While we leverage flash attention, our models don't take advantage of newer techniques like fill-in-the-middle, FIM, or multi-query attention, MQA, even though they may potentially enhance performance and efficiency. During the pre-training and fine-tuning stages, we combine our datasets into a single array, using the end-of-text token to separate different files. Our models are trained on sequences of 2048 tokens, sliced from our dataset array, and aim to predict the next token. To optimize our models, we use AtomW in conjunction with FP16 training. The learning rate follows a linear warm-up and linear decay schedule, while both the attention and residual dropouts are set to 0.1. Training is executed on 8 NVIDIA A100 GPUs using deep speed. Our base model, Phi1 base, was pre-trained in less than 4 days. Fine-tuning this model to create the Phi1 took an additional 7 hours, using the same hardware setup. Section Summary. The model architecture for the Phi1 model consists of a decoder-only transformer model with 24 layers, 32 attention heads of dimension 64 each, and a hidden dimension of 2048. The smaller Phi1 small model has 20 layers, 16 attention heads of dimension 64 each, and a hidden dimension of 1024. Both models use flash attention implementation of multi-head attention and MLP layers in parallel configuration. The models were trained on sequence length of 2048 with next token prediction loss, using FP16 training with AtomW optimizer, linear warm-up linear decay learning rate schedule, and attention and residual dropout of 0.1. Section: Pre-training. In the initial stage, which we refer to as pre-training, we employed the model we named Phi1base and trained it using the code textbook dataset. This dataset is a carefully filtered collection of code language corpus and synthetic textbooks. Our pre-training setup included an effective batch size of 1024, taking into account both data parallelism and gradient accumulation. We also applied a maximum learning rate of 0.001, which gradually increased over the first 750 steps. Alongside this, we implemented a weight decay of 0.1. We repeated this process for 36,000 steps in total. A snapshot of the training progress, or checkpoint, was captured at the 24,000th step. We designated this checkpoint as our Phi1base. To provide some context, reaching this stage is comparable to completing 8 rounds, or epochs, of training on our code textbook dataset. In total, this involved slightly more than 50 billion training tokens. Despite the modest size and computational effort, this model yielded a satisfactory performance of 29% accuracy on the HumanEval assessment. Next came the fine-tuning stage. In this stage, we refined our Phi1base model, now renaming it to PHI1. The refinement was performed using a different dataset called the CodeExercises. Although the setup for the fine-tuning was identical to that of the pre-training stage, we altered a few hyperparameters. We reduced the effective batch size to 256 and decreased the maximum learning rate to 0.0001, with a warm-up period spanning 50 steps. Additionally, we adjusted the weight decay to 0.01. The fine-tuning process was executed for a total of 6,000 steps. Throughout this process, we saved checkpoints every 1,000 steps. Eventually, we selected the most promising checkpoint from these saved points to serve as our finalized PHI1 model. Section summary. The Phi1base model was pre-trained on the code textbook dataset with an effective batch size of 1024, maximum learning rate of 1E3, and weight decay of 0.1 for 36,000 steps. The Phi1base achieved 29% accuracy on HumanEval. The Phi1 model was fine-tuned on the CodeExercises dataset with an effective batch size of 256, maximum learning rate of 1E4, and weight decay of 0.01 for 6,000 steps. Section 3 Spikes of model capability after fine-tuning on CodeExercises. In this section, we delve into an interesting observation we made regarding a significant improvement in our model's capability after fine-tuning it on a dataset called CodeExercises. Although this dataset is relatively small, having less than 200 million tokens, it consists solely of brief Python tasks that use basic Python libraries. What's more intriguing is the fact that this fine-tuned model demonstrated considerable enhancement not only in executing tasks found in the CodeExercises dataset but also those that are not included. This means the model was able to handle complex algorithmic tasks and use external libraries, showing that the fine-tuning process seems to have aided in structuring and solidifying the knowledge obtained during the pre-training phase. This occurred even if such knowledge wasn't explicitly embedded in our CodeExercises dataset. In the following, we'll compare and contrast the capabilities of our fine-tuned model, which we'll refer to as Phi1, and its pre-trained base model with 1.3 billion parameters, which we'll call Phi1base. One of our observations was that fine-tuning improved the model's understanding. We designed a simple Python function and noticed that the fine-tuned model, Phi1, was far better at adhering to and understanding the instructions. In contrast, the base model, Phi1base, had a hard time with logical relationships in the prompts. To illustrate, we gave the models a prompt involving a game between 3 characters, Alice, Bob, and Charles. The game rules involved selecting random numbers within specified ranges and scoring based on the divisibility of certain calculations. The fine-tuned model, Phi1, showed a good understanding of the problem and generated an accurate solution. It correctly simulated the points for Alice and Bob over 30 iterations of the game based on the given rules. On the other hand, the base model, Phi1base, struggled with the task. Its implementation didn't reflect an understanding of the rules and couldn't simulate the game correctly. Interestingly, a smaller version of the model with 350 million parameters, which we call Phi1 small, showed some comprehension of the problem, though it still produced an incorrect solution. These results underscore the effectiveness of fine-tuning the model on the CodeExercises dataset, even when the tasks to be solved are not explicitly present in the dataset. It hints that the fine-tuning process is crucial for the model to be able to restructure and consolidate the knowledge it obtained during the pre-training phase. Section summary. The model's capability significantly improves after fine-tuning on the small CodeExercises dataset, which consists of short Python tasks using only basic Python libraries. The fine-tuned model exhibits a substantial improvement in executing tasks that are not featured in the fine-tuning dataset, suggesting that the fine-tuning process helped the model in consolidating the knowledge acquired during pre-training. The comparison between the fine-tuned model and its pre-trained base model shows that the former has a higher level of understanding and compliance with instructions, as demonstrated by a simple Python function. Section 3.2 Fine-tuning improves the model's ability to use external libraries. In Section 3.2, we highlight that refining our model enhances its ability to effectively utilize external libraries like Pygame and TKinter. This result was unanticipated, given that these libraries are not included in our training exercises. It implies that the fine-tuning process not only optimizes our model's performance for the tasks we aim at but also facilitates its adaptation to unrelated tasks extracted from its pre-training. An examination of the range of package imports in our dataset, as shown in figure, not provided, corroborates this. To illustrate this further, we delve into an example involving Pygame. The task is to develop a Pygame program where a ball moves according to specific rules. In each iteration, the ball's x-axis position is adjusted by a random integer between -10 and 10, and its y-axis position by a random integer between -20 and 20. The ball's coordinates should remain within 0 to 400 on the x-axis and 0 to 600 on the y-axis. When the space key is pressed, the ball's x and y coordinates should be set to 200 and 400, respectively. The main code loop of a straightforward Pygame program that bounces a ball on the screen is shown. The function phi1 accurately applies the Pygame functions to modify and render the ball, following the prompt's guidelines. However, the phi1 base and phi1 small functions show correct syntax but miss the mark in terms of semantics. Specifically, phi1 base demonstrates some capacity to utilize the correct API calls, but it does not adhere to the logic of the task. Conversely, phi1 small, after fine-tuning, understands the task's logic but lacks the capability to learn the correct function calls. Section Summary. The section demonstrates that fine-tuning on CodeExercises improves the model's ability to use external libraries such as Pygame and TKinter, even though the exercises do not contain these libraries. This suggests that fine-tuning not only improves targeted tasks but also makes unrelated tasks easier to distill from pre-training. The Pygame example shows that while phi1 correctly applies the Pygame functions, phi1 base produces syntactically correct but semantically irrelevant function calls, and phi1 small after fine-tuning understands the logic but lacks the capacity to learn the correct function calls. Section TKinter example. Let's talk about a simple graphical user interface application created with TKinter. In this case, we're building an application with two key features, a suit button and a recover button, both interacting with a text field. When you click on the suit button, the application is supposed to retrieve the text from the text field, save it to a global variable named s. If the text contains the word pew, the text field should be updated to show pew pew pew. If the word pew is not present in the text, the phrase no pew should be appended at the end of the existing text. Next, there's the recover button. When clicked, this button should replace whatever text is currently in the text field with the text stored in our global variable s. It seems, however, that some models struggled to correctly apply the TKinter API in this example. The models named phi1 base and phi1 small didn't use the correct TKinter functions, leading to nonsensical function calls. Conversely, the model named phi1 did a good job at setting up the graphical user interface and implementing the intended functions. The only hiccup was that it didn't quite manage to correctly replicate the exact string, pew pew pew. There are also two additional examples of this kind, featuring PyTorch and PyPlot, which you can find in the appendix. Section Summary. The section describes a TKinter application where a text field is updated based on user input. The application has a suit button and a recover button, and when the suit button is pressed, the text in the text field is updated based on whether it contains the word pew or not. When the recover button is pressed, the text in the text field is replaced with the saved global string. The three models' completions show varying levels of success in understanding the prompt and implementing the correct TKinter APIs. Section Chat Mode Example. In this part of the research, we're discussing an AI model known as PHI-1. We discovered that phi1 outperforms another version of the model called phi1 base. Interestingly, we found that even though chat data was only used during the initial training and not during the fine-tuning, the phi1 model was better at engaging in conversation. We'll use an example to illustrate this. Imagine a student asking a teaching assistant, Ta, how to increase the resolution and rotate a graph created using Python's PyPlot library. Phi1's response would be detailed and specific. It would instruct the student to set the DPI parameter for the desired resolution, for example, to 300 for a 300 dpi. It would then advise the use of the rotate function from the matplotlib pyplot module to rotate the plot 90 degrees clockwise. Phi1 would even provide an illustrative code snippet. The Phi1 base model, on the other hand, would provide a more general response, suggesting the use of the setP function to set the resolution and the set_rotation function to rotate the plot. Given the above, it's clear that Phi1 displays a superior ability for chat. Now let's discuss the model's performance on non-standard issues assessed using a language learning model, LLM, grading system. There was a concern that PHI-1's excellent performance on the HumanEval test could be due to memorization from the CodeExercises dataset. So, we investigated this possibility. To avoid any bias or leakage, a team within our group, who did not have access to the CodeExercises dataset or the final model, created 50 new problems similar to those on the HumanEval test. They were specifically instructed to design problems that would be unlikely to appear in real-world code or coding exercises. Evaluating language models on coding tasks can be tricky. The model's output is often binary. It either passes all the unit tests or fails. This, however, overlooks the model's performance nuances, like minor errors in almost correct code or completely wrong code that still manages to pass some tests. A more insightful way to assess the model's coding skills could be comparing its output with the correct solution, and grading it based on how closely it aligns with the expected logic. This would be similar to how a human is evaluated during a coding interview, where the interviewer scrutinizes the code's reasoning and quality. For evaluating solutions, we decided to use GPT-4 to grade the solutions. This strategy gives us two benefits. 1. We can utilize GPT-4's knowledge and generative abilities to get a more detailed understanding of the student model's coding capabilities. And 2. It removes the need for designing rigorous sets of tests. We instructed the language learning model, LLM, to evaluate a student solution and assign grades from 0 to 10. The grading process began with a brief verbal evaluation followed by numerical grades. When tested on our new unconventional problems, the ranking was consistent with the HumanEval test results. Phi1 scored significantly higher than a competing model called StarCoder. As these new problems had no chance of being part of the training data and were intentionally designed to be beyond the training distribution, these results strongly support PHI-1's performance validity. Section Summary. The section discusses the evaluation of Phi1's chat capability and its performance on unconventional coding problems. The authors created 50 new problems that were unlikely to appear in real-world code bases or coding exercises to minimize bias and leakage. The results show that Phi1 achieved a significantly higher score than StarCoder on both HumanEval and the new unconventional problems, increasing confidence in the validity of PHI-1's performance. Section 5. Data pruning for unbiased performance evaluation. We noticed a significant improvement in our model's performance on the HumanEval benchmark when we trained it using the CodeExercises. Believe provides deeper insights than the conventional contamination studies often found in academic literature. The latter typically relies on measuring the overlap between training and test data. See section 4.8 for an example. However, to cover all bases, we initiated this section with a traditional contamination experiment. The findings indicate that the CodeExercises dataset is not contaminated by HumanEval in the usual sense. Section Summary. The authors observed a significant improvement in the model's performance on the HumanEval benchmark after training on CodeExercises. To investigate this boost, they pruned the CodeExercises dataset by removing files similar to those in HumanEval, which resulted in a more than 40% reduction in the dataset. Despite this aggressive pruning, the retrained model still outperformed StarCoder, indicating that data pruning is a fairer way to evaluate performance than standard contamination studies. Section 5.1 N-gram overlap. In this section of our study, we explore two methods of textual analysis, N-gram overlap and similarity assessment using embeddings and syntax. Firstly, we look at N-gram overlap. This approach measures the similarity between texts by identifying shared sequences of words. We applied this method to our CodeExercises dataset by comparing each question and corresponding exercise. We discovered that there were 4 instances where there was a 13-word sequence overlap with entries from our dataset. However, upon closer examination, we discovered that all 4 were false positives, indicating that our dataset doesn't have significant verbatim overlap with the HumanEval dataset. Moving to the second method, we noticed that N-gram analysis alone wasn't sensitive enough to identify similar code snippets between the HumanEval and CodeExercises datasets. Therefore, we adopted a combined approach using embeddings and syntax-based analysis. For the embedding analysis, we computed the L2 distance, a measure of similarity between the embeddings of code snippets. These embeddings were obtained from a pre-trained CodeGen Mono 350M model. We found that this method effectively captured code pairs with similar semantics, which we could infer from Python DOC strings, function, class names, and code structure. For the syntax-based analysis, we calculated the string edit distance between the abstract syntax trees, ASTs, of two code snippets. This analysis successfully spotted overlapping segments between code pairs while ignoring non-syntax elements like variable, function names, comments, and Python DOC strings. To prune our CodeExercises dataset, we set a threshold for the embedding distance and tested several match rates for the AST distance. We've provided examples of code pairs identified by these methods in an appendix. We varied our match rate between 0.95 and 0.8, leading to the exclusion of 42.5K to 354K problems from the total of 879.5K problems in CodeExercises. Our retrained model, Phi1, was then tested on these pruned datasets. We compared its performance with the original Phi1 trained on the full CodeExercises dataset and with a model prompted by the 15.5b parameter star coder. We classified the HumanEval problems into two categories, similar and non-similar, based on whether they closely matched any problems in the original CodeExercises dataset. We then evaluated the accuracy of the models on each subset of HumanEval. Our findings show that even after substantial pruning of our dataset, PHI-1 consistently outperformed StarCoder prompted by a significant margin. This affirms that our improved performance is not due to data contamination. Furthermore, it's worth noting that the model's accuracy was lower on the non-similar subset of HumanEval compared to the similar one. Section summary. The authors used n-gram overlap and embedding and syntax-based similarity analysis to prune the CodeExercises dataset. The n-gram overlap analysis was not refined enough to find similar code snippets, so they used embedding and syntax-based distances instead. They fixed a threshold for the embedding distance and tested several match rates for the AST distance, which resulted in heavy pruning of the dataset. Despite this, their retrained Phi1 model still outperformed the 15.5b parameter star coder prompted model, validating their performance boost.